Good morning, life scientists. Today, we're going to have a video where I'm going to go over some notes that I've provided regarding what you read. And I know you'll be so sad that I'm not in the video, but the quality from the Chromebook videography is poor, and I really want to make a better one using my phone, and I don't have a selfie stick. So today we're going to talk about energy. And the big idea here is that energy can change from one form to another without net gain or loss. You probably know that as the conservation of energy law, that energy cannot be created or destroyed. It can only be transformed from one form to another. So we start off with this idea of work, okay? And work is done when a force acts on an object and the object moves in the direction of the force. So that can be put into an equation, W, which is capital, equals capital FD. Work is force times distance. Okay, I wrote that out here. Here's the variables. Here's the word equation. When we look at the units for that, we get forces in the form of a Newton, distance is in meters. So the unit is a Newton meter, okay, which I've written here. But what we call that is a joule. And I'm sure you've probably heard of that phrase before. Okay, there are two categories of work. Work that's done against force and work that's done to change the speed of an object. Work that's done to change a speed of an object. Remember, changing the speed of an object is acceleration. So work done to either accelerate or decelerate an object. Okay, that brings us on to the next topic, power. Power is the rate at which work is done. Remember, a rate of something has to do with time, per elapsed time. How much time does it take to do that work? And what we call that in a equation is power is work over time. Okay, and that is joules per second. That's a joule per second. So joules per second, we're going to know as a new unit called watts. W-A-T-T, a watt. Okay, you've probably heard that in terms of how powerful a bulb is, a light bulb. Okay, 60 watt bulb. When you have a three-way bulb, it's usually something like 50, 100, and 150 watts. They get brighter and brighter and brighter. So the higher the watt, the higher the power, the brighter the light. It all relates to each other with that conservation of energy. We also can look at this in the terms of an engine. This is another place that you might have understood this topic. A high power engine, it means that it does work rapidly versus a low power engine, okay? In the United States, we call engine power horsepower. And the conversion that you can use for that is that 1 HP or 1 horsepower is equivalent to 0.75 kilowatts. Remember, kilo means 1,000. Okay, so 1 kilowatt is 1,000 watts. And we measure electricity in kilowatts. So the electricity company sends you a bill for your house, and it's usually telling you when they read your meter how many kilowatts of energy did you use. Okay, so that is a review of energy and a review of power. Now we're going to talk a little bit about how we use that a little more specifically. Okay. Mechanical energy is the property that enables something to do work. Okay. Rather, the property that enables something to do work is called energy, and energy is measured in joules. So mechanical energy is basically due to the position or movement of something. Okay. So the property that lets something do work is called energy. In order to have something have work, you have to put energy into it. Okay, there's two things that energy has to do with: position and movement. This should definitely be a review from 8th grade science. Positional energy is known as potential energy. It is stored energy, or what we call held in readiness. And something that has potential energy has the potential to do work, but it's not currently doing work. There are 3 types of this: elastic, chemical, and gravitational. Elastic potential energy, EPE, is like when you compress a spring. While you push a spring down, it's got the potential to have energy, which won't be released until you let the spring go. Pulling back a rubber band to shoot it isn't being transformed into motion yet, but it has the potential to be. Think about if you pull the rubber band back a little bit versus a lot, what kind of energy that results in. Same thing as with using a bow, an arrow. When you pull back the bow, you are increasing the potential energy of the system. Chemical potential energy, or CPE, is energy stored in the bonds that hold a compound together. You learned about this back in 7th grade science when you talked about glucose, C6H12O6. That is processed in the mitochondria of your cells during cellular respiration, and the energy that's released is called ATP. So glucose has stored chemical energy that is released into the form of usable energy once it's processed by your body. Okay, making bonds stores energy, breaking bonds releases energy. What we're going to talk about is gravitational potential energy, which is basically has to do with the height that an object is elevated above the surface of the earth or above the surface at which it's going to drop to. Potential energy, gravitational potential energy, the equation for it is mgh, mass times gravitational force times height. So it is a function of gravitational force, which means on another planet or the moon, it may vary. Mass is in kilograms, gravitational force is in meters per second squared, and height would be in meters. This is an equation you're going to need to use today to solve problems. Okay, let's take a look at kinetic energy. Kinetic energy is energy of motion. Something that's kinesthetic, is moving. Kinetic energy is the work required to bring an object to rest. So think about it, if something's moving, it's what requires to stop it from moving, okay? Kinetic energy is known as 1/2 mv squared. Half the mass of the object in kilograms times its velocity, meters per second, squared. The whole thing is not squared, just velocity is squared. Okay, so when you do the math, this is an important equation to use today. We can also say that if kinetic energy is the amount of work required to bring an object to rest, then kinetic energy must be equal to the work that was being done to move the object, which is FD. Okay, we said that earlier. Work is force times distance. So you can set these two things equal to one another. Kinetic energy is equal to the work, and you get this equation. The force in newtons times the distance in meters is equal to 1/2 the mass times the velocity squared of the object. Again, necessary for today's assignment. Okay, the last thing we're going to talk about today is the work energy theorem. This is the relationship between work and energy. Whenever work is done, energy is changing. You do work, you change the kinetic energy. The thing I want to go over that can sometimes be confusing to people is that when something is moving in a constant motion, in a straight line, constant velocity, for example, you push a box across a floor at exactly enough force to overcome friction, so it's moving at a constant rate. Remember, the net force is 0. And if net force is 0, and you know that the work is equal to the kinetic energy, if you have a 0 net force, you actually have no change in kinetic energy. So something moving in a constant speed doesn't necessarily have a change in kinetic energy. Because it's constant, its energy is not changing, and it would be 0. Sometimes students have a hard time understanding that concept. Last thing I want to talk about today are the hidden forms of kinetic energy. Energy in motion that you don't quite see with your naked eye. Heat, which is random molecular motion, okay? Sound, the vibrating molecules in a rhythmic pattern we learned about, okay? That's those rarefactions and compressions and areas where sound is moving through the medium like air. Light is motion of electrons in the atoms are being emitted. Light is emitted when electrons move inside of an atom. And finally, electric currents. All examples of kinetic energy that you might not realize are. All right, today you're going to work on the problem set I gave you, they are not requiring many changes of manipulations of things. So go ahead and do a great job on that today. And please use the SKYS method for full credit.